So test 3 is due a week from today, right? Our final is a week from today. So I think today I'm just going to talk about chapter 5, chapter 6. We'll say, we're not going to do all of chapter 6, but we'll say what we need to say about chapter 6 on Wednesday, which will also be on YouTube television. I'm not sure on this. Now it's funny because this is a video. And if you've been videoed, you know what the story is, right? Especially if it's one take. To think about every word you say, because people could be watching this 100 years from now. She'll do a better job. But I guess you'll not meet very many people from 100 years ago. So first we want to talk about the roots, well, the multiplicity of a root. So maybe we said it here and we'll say it again. Maybe we'll say it another way so it'll be easier to see. We say A is a root of a polynomial with multiplicity n if x to the n divides p of x by x to the n plus 1. Maybe we could say easier. So I wrote this, easier is maybe this, because here you can see. Maybe if we were to say the definition, if p of x. Question or comment? Now's the time to be quiet, right? Now we'll get back on.
Oh, sorry.
If you have a question or comment, let us know.
Sorry.
Maybe easier if you could say if p is equal to x minus a1 to the n1 times x minus a2 to the n2. X minus a m to the nm. Then the roots of p are a1, a2, and n with multiplicity. N1, N2, and N. Respectively. And we should say something, note. So when I wrote this, all the AIs are distinct. Because if they're repeated, then you can get the right number for the multiplicity. I think maybe it's the easy way to see. Maybe say, for example, what are the multiplicities? What are the roots and multiplicities? X minus 2 to the third times x to the third to the fourth times x to the fourth. Questions or comments? So we'll say again, for all the people in the present and maybe distant future. Have a class today, we'll have another YouTube class on Wednesday when we'll talk about chapter 6. All of chapter 6 we'll talk about, or all that we need to know about chapter 6 we'll talk about on Wednesday, and we'll finish what we need to say about chapter 5 today. We'll have some review sessions. I guess what? I reserve the right to say cut and to stop. But that's for people in the present. But right now we could broadcast almost everything. So we can say, for example, like we want to understand the roots and the multiplicity. So what are the roots of this polynomial? And what are its multiplicities? Like the reason I wrote this is because if someone wrote this, someone wrote x to the 1 to the 7 times x minus 1 to the 8. Someone would say, oh, well, 1 is a root of multiplicity 7 and 8. No, that wouldn't be right. That's why we want the AIs to be distinct. We have this, we should write this as x minus 1 to the 15. Then 1 would be a root of multiplicity 15. Yes? Yes.
Mm-hmm.
Yeah. This is the second class. The reason we had the second class is
I
because
thought that class was moved to 140.
what we're doing is this. We had our usual class at the usual time. And we have to make up 2 classes. So we still make up 1. I gotta watch my fingers, especially since I'm a kid. Number 1 was gonna be for the reading day, and the other one was today. That seemed the time when most people could make it. And we have the work of Mr. Ng for the people who can't make it. And you can always go back and watch this too, right?
Mm-hmm.
So here we could say, like, you know, the whole thing about this theorem is it's factored nicely. It's easy to read the roots and the multiplicity. So what are the roots of this polynomial and its multiplicities? I don't know. It should be, what does root mean? Some people used to call it the zeros. Maybe it's more suggestive. The roots are the numbers which make this, when you put it to evaluate this function, you get a 0. So what are the roots of this? Like, that's why they wrote it this way. You can say, oh, the roots are A1, A2, AM. What are the roots of this one? Should be easy to see. Roots are 2, 3, and 5, right? No, 2, 3, and minus 1. Plus 1. If I put a 2 in there, the first place would be 0. Put a 3 in there, it'll be 0. If you put a 1 in there, it'll be 0. And the multiplicities are are 3, 4, and 5. Respect. So if it's a nice form, it should be easy to read off the roots and their multiplicities. If he makes it, you know, complicated, maybe it's to find the roots. And multiplicities of x minus 1 to the 7 times x squared minus 1 to the 4th. We have to do some work, right? Because here it's not in a nice form like it is here. Maybe this part is, but I have to do something about that. How do I factor x minus 1 squared?
X parentheses x minus 1. Oh no.
Wait, what is it?
I was gonna say x parentheses x minus 1, but then I thought about it. No.
Wait, how do I factor x minus 1? X squared minus 1 is
Yeah, x minus 1, x plus 1. Yeah.
x plus 1.
Yeah. Because you get x squared and then 0 and then negative 1, yeah.
Good. So now what? So this is equal to x minus 1 to the 7th times x minus 1 to the 4th times x plus 1 to the 4th. Right?
Mm-hmm.
And now, so this is equal to x minus 1 to the 7 plus 4 times x plus 1 to the 4. So what are the roots and their multiplicities?
1 and negative.
You're not following me? I expected you to go.
Sorry.
It's okay. So what are the roots and the multiplicities?
So the roots are 1 and negative 1.
Yeah.
And the multiplicity is 11 and 4.
With multiplicities. 11 and 4, respectively. So why do we bring this up? Because we said, well, suppose the characteristic equation has repeated roots or root multiplicity, are we going to have the right number or the multiplicity number of eigenvectors? And we saw the answer was no. So maybe we could say, because first we should say this, like if we have an eigenvalue, we have to have an associated eigenvector. We have to. But if we have an eigenvalue with multiplicity 2 or more, not necessarily. This was our classic example. So maybe we say if lambda is a root with multiplicity 2 or more, does it have 2 or more independent eigenvectors? And we saw the answer earlier today was no, right? Maybe we could say, because these two, and the answer was no. You'd say, recall this matrix has characteristic equation 1 minus lambda squared is equal to 0, as does 1, 1, 0. I don't know, I could try as does period. People in the future. See how sentences were composed in the past. Now what? Maybe we should explain why. What's the characteristic equation of the first? We say it's 1 minus lambda 0, 0. 1 minus lambda determinant of. So that's equal to 1 minus lambda squared. Is equal to 0. Is the characteristic equation, right? And for the second, the characteristic equation is 1 minus lambda 1, 0, 1 minus lambda. That's exactly the same thing, right? We get 1 minus lambda squared minus 0 times 1, we get the same thing. But what's the difference? What's the difference? Find the eigenvectors. 4, 1, 0, 0, 1. Every non-zero vector is an eigenvector for this, right? Maybe most natural is question.
Why did you turn it into x minus 1? Like, it goes from x minus 1 to the 7, and x minus 1 to the 8. You turned that into...
Well, because what? This? Because here we factored this as this, right? X minus 1 squared is this, right?
No, but why do we turn it from 2 to 1 and then from 1 back to 2? Is it because we need 1 to be a positive and a negative up top?
No, here I factored this, right? X minus 1 squared is x minus 1, x plus 1, right?
Yeah.
And then this is all to the fourth, so this becomes x minus 1 to the fourth, x plus 1 to the fourth, right?
Yeah.
And now what? Now I combine, kind of like terms of x minus 1 to the 7th times x minus 1 to the 4th becomes x minus 1 to the 11th times x plus 1. And why did I do this? Why did I put it in this form?
Yeah.
Because when it's in this form, I can read off the multiplicities most easily.
Oh, okay.
Like when someone gave us something like this, we were like, this was not so good for reading off the multiplicities. We have to do a little bit of work.
So it would be as if like the negative ones, like if we would have put the roots are negative 1, and then the multiplicities are 7 and 8, that would be wrong.
That would be wrong, right? Because here, that's why, this is really a nice form if the AIs are distinct. If all the roots are different, then it's really easy to read off the, but if he does something like, like this, or, something where you have like the same root hidden, then you have to do some work. But here, this is like the nicest way, like what's in this form, it's easy to read off the roots and the multiples. Do you remember this from pre-calculus? What do you remember from pre-calculus? What do you think the man from the future remembers from pre-calculus? I think they'll be teaching pre-calculus 100 years from now. I never took pre-calculus. I'm not telling the truth. But when I went to school, they just called it algebra and trigonometry. All right, so now what's the next thing? We want to find the eigenvectors for this. Maybe recall lambda is equal to 1 is the eigenvalue. So we get 0, 0, 0, 0. X is equal to 0. Any non-zero vector will do for an eigenvector. The only reason I said non-zero vector is why? Because our eigenvectors have to be non-zero. We continue. Eigenvectors aren't necessarily unique, but the dimension of like the eigenspace is. What's the dimension of the eigenspace? You find a basis for the eigenspace. It's the number of vectors in the basis. So here, so we can take that, and for our second matrix, which has the same characteristic equation, we say we want to solve this, right? We subtract 1 from the main diagonal, so multiplied by, I'm going to say x1, x2 is equal to 0. This whole thing is equal to x2, 0. So that means that x2 is 0, no vector. Right? You guys have to do me a favor, right? If I make a mistake, you really have to tell me, because think about what the people in the future will think. Now what? X2 is 0, so actually, so what? We could say this is an eigenvector. And I can't find, so eigenspace, we could say E1, for example, has dimension. Only 1. Here. And what does E sub 1 mean? E sub lambda maybe in general means a set. You know, we have a matrix associated with this, the set X, such that AX is equal to lambda X. So here what? We can have an eigenvalue with multiplicity 2 or bigger, but the associated eigenspace doesn't have dimension, has a smaller dimension. Some people would say that kind of eigenvalue is defective. That's actually a formal definition. So maybe we should do 1 or 2 like, kind of examples. Find it, because what will definitely be on the final is something like finding eigenvalues for this matrix, finding associated eigenvectors. Maybe that is this matrix diagonalizable and such. Remember we said a matrix is diagonalizable when it has n independent eigenvectors. Maybe I should do some true and false questions first. What do you think? So an n by n matrix is diagonalized with n independence. Which is why we're talking about what we're talking about. Because if I have n distinct eigenvectors, necessarily it's diagonalizable. Should we say something about complex eigenvalues? Did I hear yes? We should, just for the sake of culture. Maybe we'll have a discussion later about whether we'll put it on the final. But we should be able to do it just for the sake of like noting it for the future. How much we'll put on the final, we'll have a discussion about it. So, and remember we said if A is diagonalizable. If A is diagonalizable. Well, I could say PA. A is equal to P, D, P inverse, where P is a matrix whose columns are eigenvectors. And remember why we did this? We said, like, if A is diagonalizable, if A is a diagonal matrix, D to K is comparatively easy to find. While if we just an arbitrary matrix, let's say B to the K might be a big nuisance. Not really hard, but a nuisance. So here this thing simplifies the procedure. It's hard to say what a matrix does in general. But once you have some eigenvalues, you get an understanding, or a better picture of what it does. Maybe we could say, here's one or two from the book. If P is equal to, let's do the easy ones. I'll do the ones. If P is equal to 5, 7, 2, 3, D is equal to 2, 0, 1, 0. Find 8 and 4. Maybe let's add some more. 8 and 4. So what do we do? What do we need? And we should also say, comma, A is equal to P, D. So maybe first we should say, what is the inverse of P? If P is equal to 5, 7, 2, 3. How do we find the inverse of P? We have several ways to do it, right? Maybe we'll argue that we have learned 3 ways, but we've definitely learned 2, right? One way is we can write the identity and row reduce. Second way is the cofactor way. And the cofactor way is a more general case of what the author notes in the first section of matrices. He gives a formula for 2 by 2. Did we learn that matrix? Did we learn that formula? Were we told to learn that formula?
Yes.
No, that's not true.
No.
I said don't learn it because you got enough things to remember. And we learned this better method in section 3.3, this cofactor method, which will say how to find the inverse much faster, or in general, for bigger matrices. So maybe we'll say Cij here is equal to, this will be 3, this will be minus 2, this will be minus 7, this will be 5. And so Cij transpose is equal to 3 minus 7 minus 2. 5. Is that the inverse?
Yeah.
Well, we should verify one thing. What's the determinant of P?
And 1.
1. So this is the inverse. Remember, this thing divided by the determinant of A is A inverse. And here, sorry, here our matrix is P right now. So here we could say, well, A is supposed to be P, D, P inverse. So what is A to the 4th? You may say, why is he like this form so much? Well, we could say a to the fourth is equal to p d p inverse once, p d p inverse twice, p d p inverse 3 times, p d p inverse 4 times. What happens? What's p inverse times p? I. So this goes away. Again. So this is just equal to p. There's 4 d's left, so we'll call it d to the fourth p inverse. So this is equal to, well, p is p. 5, 7, 2, 3. D, what's d to the fourth? 2, 0, 0, 1 to the fourth times p inverse. 3 minus 7 minus 2, 5. What's the middle matrix?
16, 0, 0, 4.
What's 1 to the fourth?
No,
1.
1. So what do you want to multiply? The first 2 or the last 2 first? And does it matter?
First 2?
First 2. Does it matter?
No.
Doesn't. So what do we get? We get 5, 7. It's 5 times 16. 7, 0. 5, 7. 7. 2, 3. 2 times 16. 3. Good?
Wait, so we're only multiplying the first column by the first number in the...
What's up?
So you multiplied 5 to 16. How come you didn't do 7 to 16 also?
Well, what do? How do I multiply matrices? I multiply this? Well, when I say multiply,
Oh. It's,
We-
okay, I see
really
that.
should be saying dot product, right?
Yeah.
Remember, we can multiply matrices, we can multiply matrices times vectors. But vectors times vectors only if things are lined up. But this is what? This is what we call a dot product. 5 times 16, 7 times 0, 7 times 0 left is 0. This is 5 times 0, 7 times 1 is 7. This is 2 times 16, 3 times 0. It's 2 times 16. Now this one may be more complicated. This is 5 times 3, 15 times 16 times 7 times minus 2. The second one is minus 35 times 16. Minus 35. Right? This is what? This is, for the second one, what do we get? 6 times 16 minus 6. And the last is minus 14 times 16 plus 15. Good? Should we simplify that? How can we simplify that? And I would say in general, like, you usually should leave it in terms of, so if the next one's going to be really big, I almost feel the next one I should leave as an exercise. But all of this, I'm still like a half hour. Let's do some true and false. Maybe you can see how you think, or how the viewer thinks the answers are. And we'll say what the right answers are in a second. If A is diagonalizable, then A is equal to, we're assuming A is n by a matrix, then A is equal to P, D, P inverse for some. Who thinks it's true? We have one true, two truths. I can't tell. Who thinks it's false? Nobody? Wait, someone else. Anyone else for true? Anyone else for false? You're for true or false?
True.
So we have two truths, one false. Good, this one's true. That's the definition of diagonalizable. There's a matrix P such that A is equal to P, D, P inverse. We should say where D is for some diagonal matrix. For some P and diagonal matrix. I know. I didn't do 8 to the 40th. That's a good exercise. They always say for the reader of the book, but this is a good exercise for the viewer, right? Let's see, how about the second one? If Rn has a basis of eigenvectors of A, then A is diagonalizable. That's the first one. B says, if Rn has a basis of eigenvectors of A, then A is diagonalizable. Who thinks it's true? Only one? Who thinks it's false? One true and two falses. It's true. That's what you're looking for. You're looking for this basis of eigenvectors. That's what your P is going to be. Your P is going to be a matrix whose columns are those eigenvectors. And the problem with the defective ones, defective means you don't have enough eigenvectors. You have multiplicity, say K, but you don't have K independent eigenvectors. If A is diagonalizable if and only if A has n eigenvalues counting multiplicity. Let's write that here. A is diagonalizable if and only if A has n independent, not independent, n eigenvalues counting multiplicities. So what does he mean counting multiplicities? You could have like, for each eigenvalue, which thing do we say? If you have an eigenvalue of multiplicity 2, you count that as 2, not 1. If you had an eigenvalue of multiplicity 5, you count 5, not 1. Who thinks that's true? Nobody. Who thinks that's false? Nobody. This is false. False is right. Maybe say here's a little mystery for the viewer. How many people you think are in the room? We'll never tell. This is false, right? This was our first example. That 1, 1, 0, 1 matrix had multiplicity 2. So say 2 eigenvectors, 2 eigenvalues counting multiplicity, 2 eigenvalues counting multiplicity. But it didn't have, but the matrix is not diagonalizable. Remember, we can go back to these two. This matrix is diagonalizable. You may say, duh, it's diagonal. But this one is not. This one we did all this work to say there's only one independent eigenvector, or maybe a better way to say it is the eigenspace is dimension 1. So I can't find a second eigenvector, so I can't diagonalize. Let's see. Oh, here's a good one. If A is diagonalizable, so one word, then A inverse exists. Who thinks it's true? Who thinks it's false? False is right. Why is it false?
Because like if it's like a zero vector,
What?
if it's a zero vector, right, it would be invertible. I mean, a zero matrix. I mean, not vector.
Yeah, that's why. Maybe you could say the short reason why this is true is, for example, take this example. This matrix is diagonal. Diagonalizable, the whole deal. You can pick any vectors. You can have any P you want. But it's not invertible. Why is it not invertible?
Because the determinant is zero.
Yeah. What's our favorite theorem in this? Well, what's one of your favorite theorems in this class? We could ask the viewer. I almost feel like it's a weird question. No one asked your other professors and ask you what's your favorite theorem, your second favorite theorem, or something like that. So what else should I say? What else should we say about chapter 5 before we move on? We should say something about complex numbers. We should ask people, how many people have heard of complex numbers? I'm going to give away the... Who have not? Oh, everyone has heard of complex numbers. Beautiful. But quick, a brief review, and we'll say one or two things about complex numbers and matrices. Maybe that will be all we'll say today. Unless you guys want more. What's the fundamental theorem of algebra? It says that if P of x is a non-constant polynomial, then P has a root. Right? How many people remember this from previous class? Nobody. Maybe that's why I'm math education say that. So now what? Maybe you can say, what are you talking about? X squared plus 1 doesn't have a root. But when he's saying root, he's saying possibly complex. Maybe you can say, because what happened? Like something like x squared plus 1 has no real solution. So they invented something. So they said, let's call. Because if we were to try and solve this, what would we do? We'd say, oh, x squared is equal to minus 1. And then we take the square root of both sides. So x is equal to plus or minus the square root of minus 1. So we said, what's this square root of minus 1? No real number has the square minus 1. So they say, let's call I the square root of minus 1. Why do they call it I? The ninth letter of the alphabet. No, that's not the reason. It's called I for imaginary. And we'll say, and then maybe say the basic algebra. And first we'll say a complex number is one of the form. A plus B, where A and B. Good? Let me say, so maybe first we'll say addition of complex numbers is just as you expect. What do? You add like terms. So if someone gives me A plus BI plus C plus DI, add like terms. A plus C plus B plus D. How do we feel about subtraction? Oh, we don't like subtraction. If we rephrase everything in terms of addition, we can do subtraction. So we can say A plus BI minus C plus DI. We don't like subtraction. We just say A plus BI plus minus C minus DI. And then it reduces to the previous case. It was in linear algebra class I first heard said, I don't want to deal with subtraction. Just think of everything in terms of an additive inverse. But now it's become popular, you might see that in your algebra class. Let's not do 2 minus 1, let's do 2 plus minus 1. Some people feel like you're making the situation more complicated. But here in some ways you totally would get rid of subtraction, if you like it. Maybe we say multiplication. Of complex numbers. And I would say it's just like usual multiplication, except I have to remember I times I is minus 1. So I'll say A plus BI times C plus DI is equal to AC plus minus BD, or BD I squared. Collect like terms, I get AC minus BD plus AD plus BC. Should you memorize the formula? I don't think so. Just remember I times I is minus 1 and you'll be able to produce it if you know like basic algebra, the distributive law and such. And in general, that's what I would say. In math, you don't want to memorize a lot of formulas. The math isn't about memorizing formulas. Just remember just a few ideas that can take you far. I think that's true in general, but not some people might disagree. And maybe we could say so. So the thing is with all of this to say, like suppose I do, I get a matrix and the roots are complex. I still might have eigenvectors, but the eigenvectors might be complex. We should do one, right? That's a book. Oh yeah. Great. So let's try this. Find the eigenvalues. For this matrix. What do? We do what we always do. How do we find eigenvalues for a matrix? We want to find the characteristic equation. So we'll say minus lambda minus 1, 1, minus lambda. We want the determinant of that equal to 0, and find the solution to it. That's our standard way, right? We find the determinant of A minus I lambda, set that equal to 0, those are my eigenvalues. So what do we get here? Lambda squared plus 1 is equal to 0. Sound familiar? Yeah, we have lambda instead of x. And like I said, some people have accused me of saying my lambdas look like x's. Can you imagine? So here, so what are my eigenvalues? Lambda is equal to -1 squared, so lambda is equal to plus or minus I. Good? So let's do it. Which one do you want to use? I or minus I? Which one do you use? Let's use minus I. So if I put minus I picked minus I because minus minus is going to be plus. I minus 1, 1, I. So I want to solve this times x is equal to 0. What do we say is always a good thing to check when we're doing this? We should check that our matrix is singular. What does that mean?
Non-invertible.
Not invertible. So how can I check this matrix? Because if we made a mistake, this is usually true in general, not in math class, not just in math class. If you made a mistake, you want to know as soon as possible so you can fix it. Because you don't doing more work in a mistaken state, your work doesn't have much help. So now here, what do we do?
I minus I should be -1.
So actually what? So is that matrix singular? Singular is another word for not invertible.
Yes.
What?
Yes, it is.
So why is it singular?
Because I minus y is -1, and then -1 minus -1 is 0.
Yeah, you could say the determinant 0. You could also check, I mean, I would say like if I multiply what times 1 gives me I. I times 1 gives me I. And I times I is -1. So the columns are multiple of each other. You can check that the rows are multiple of each other. Whatever you like. So it's singular. So now what? How do I? So I could say. So I could say I x1 plus x2 minus is equal to 0. The second row should be a multiple of that. So I'm not going to. What do I do now? Just pretend they're numbers. Maybe you might feel a little uncomfortable. Like I don't know what I is. Something someone made up. We can pretend it's a number. Or we can pretend it's a number. So here we can say x2 is free. We'll call it s. And x1 is equal to s over I, right? Probably should remind you of a previous class. Do you like i's in the denominator? Most people don't. So I could say this is equal to, how do I get rid of the I in the denominator? I multiply the top and bottom by I. So I get is over -1, or minus is. So what does my eigenspace look like? My eigenspace, what was the eigenvalue? Minus I. Is equal to the set S2 is free, minus IS. So that's equal to, I can take out an S minus I1. So what's an eigenvector? So that's an eigenvector. Good? We substitute S is equal to. Does it feel much different than it did for real numbers? Or did it feel the same? Some people said it feels the same. Should feel the same. Should feel like the same procedure. And this procedure you should be very familiar with, because this is what we're going to do. Find the characteristic equation. Find its roots. Once you have that, you can find the eigenvalue. Subtract your eigenvalue off your matrix, you find the null space of that matrix. Let's see, for maybe say 4, lambda is equal to I. What do we want? We want minus I, minus 1, 1, minus I. Is this matrix singular?
No.
No, it should be, right? It should be what? Multiplied by minus I, multiplied by minus I. No, it should be right. Still think it's not singular? Because I was going to say, the way I was thinking is like, what do I need to multiply 1 by to get minus I? Minus I. Minus I times minus I is I squared. I squared is minus 1. So one row is a multiple of the other. If you like a constant multiple of the other, it's an imaginary constant. Some people like to make jokes about real complex problems and things like that. So now what? So since that's the case, I can just look at one equation. Maybe the second equation is easier. Maybe say x1 minus I, x2 is equal to 0. Again, x2 is free. Maybe we'll call it t, not to confuse with that. Doesn't matter, you can call it absolute if you're wrong. And now, x1 is equal to I times x2, which is equal to IT. So my solution should be T, IT, such that T is a real number. So this is EI. It's funny, think about 100 years ago. If you told them about the internet, Venmo, Zelle, I almost feel like they really should come up with better names for things. YouTube, etc. They wouldn't know what you were talking about. If you were talking about, you told them how many followers you have, followers, savior of some sort, wouldn't know what you're talking about. Now, I mean, oh yeah. Actually, we should say how many things do you think will survive for another 100 years? Just talk about the phone. Not everyone had a phone. No one had a phone except at their house. Things are different. All right. So what is an eigenvector for this space?
T.
Well, I should take out the t. It should be so 1. I'm sorry. I1 is n. So there I have my 2 eigenvectors. Are those 2 vectors independent?
Yes.
Yes. Why?
They're not multiples of each other.
What?
They're not multiples of each other?
Exactly. Remember, this criterion is only for 2 vectors or less. If neither vector is a multiple of the other, set is independent. I can't say that if I have 3 vectors. We've seen counters. Good. So maybe we can cut now.